Basics of blast wave theory. Week 5. Shock formation. Shock wave attenuation. Shock wave reflection.
Let us see this diagram. I mean, that had been drawn a bit better way. So you see, that is the first starting point. So it starts getting steeper, and it finally looks like a jump in here. So this is fully developed shock wave. We call this triangular because it looks like a triangle, and very interesting. What happens here, the density is normal. When this front passes that small zone, the density jumps and goes up. So this portion compresses the material on the right in the direction in which it is moving. But what happens behind? Behind it is relaxing. Behind it is relaxing, going down. So after some time you will see a profile like this one. Why this is happening? Now the question is why that is happening. The compression done in this zone, for example, a work had been done on the neighboring material. Now that work requires energy. Somebody had to supply the energy. So either the energy is supplied from the external world, or this poor shock had to consume what it had in its pocket. So what it do? It loses its strength. Now this phenomena, from here up till here, you can call it a shock formation, and onwards it would start losing its strength, to which we call attenuation. So the shock starts with some given energy, no external energy is being supplied, and when it is moving in a compressible medium, highly compressible, it would lose its strength very quickly. But if the medium is less compressible, then it would lose its strength slowly. Now it all depends upon the compressibility of the material. If it is highly compressible like here, then it would lose its strength more quickly. Now this attenuation phenomena, you can look in here.
Everything is called plus width. Attenuation.
Yeah.
So width, the thing is called plus width, correct?
Yeah. So this is where I was going to throw this word. Now this is some real problem calculated or simulated. So in here it is about 1 kilogram of explosive TNT, 1.2 kg to say precisely TNT, that had been exploded in here. Now if you look, these are centimeters, so this is 50 centimeter, the radius would be about 5 centimeter. So this line represents that initial situation, and this strength, I have just truncated this graph, goes up very high. It goes to 210 kilobars, while on the left scale you have bars. Now the second curve, this is first curve. The second curve is plotted 0.1 milliseconds later, and similarly 0.1 millisecond later the third and fourth, and so on and so forth. Now let me consider this one, this peak, which is plotted at 0.3 millisecond or 300 microseconds. Now this is quite visible. We see the strength is about 50 bar, 50 atmospheres. Now after 0.1 millisecond, you see the strength has gone down, and further down and further down. Now the drop is quite rapid. The drop in strength is quite rapid. Another thing you might note, that distance between this peak and this is larger than between this peak and this peak, and so on. Between these successive peaks, the distance is reducing. The time at which they are plotted is same. What does that mean? It means the velocity of the shock front is continuously decreasing also. As I pointed out, shock strength comprises of all these: shock velocity, shock pressure, shock density, shock material velocity. The material with which it is always less than shock velocity. Shock is much faster compared to the material and the internal energy, or you can call temperature also, the given energy. So now this, at least two variables you can see in this single graph, that shock velocity is continuously decreasing also, as well as the pressure. Now this continuously attenuating or losing strength shock wave is called blast wave. So this is just a name for, like, we all are human beings, but some of us are Malaysians and some are Pakistanis, for example. So all are human beings. So blast is a shock wave. Blast wave is a special category of shock wave. Shock wave can be traveling in water, can be in metal, can be in soil. But the shock wave traveling in atmosphere without any support, without any chemical energy release, further chemical energy release would be called blast wave. So when we think of or we talk of blast wave, then we cannot add energy into it. Once we say this is blast wave, okay, the blast wave moves and the movement is done at the expense of its own energy. Whatever energy was supplied to it and it got at its beginning, then it would continuously lose that energy. So when you do calculation, for example, and in numerical calculation sometimes you generate certain bugs in your computer codes, and if you see a peak rising, you must say, oh, something went wrong with my programming, so this is impossible. The blast wave had to continuously reduce its amplitude. Okay, now I talk about shock, reflection, transmission, like other waves. Please keep this in mind. I would talk in general about shock waves, and I would occasionally say blast wave. When I say blast wave, then I am confined to atmosphere only. But I have to describe this whole phenomenon. It's very important. From defense point of view, we have to deal with so many weapon systems in which explosives, they interact with metal. Of course, they interact with air also. But when we try to learn this theory, then we have to learn it in a bit general way, and then we can very easily come down to blast wave whenever it is required, because we know the limitation. What are the limitations? What are the requirements? So we can learn it. Now, this conceptually, this is important. This we have to keep in mind when we go and develop further theory. By the way, in here, I have just talked about concepts. I haven't talked about how to calculate these. this would follow later, and a bit more general development I would start with detonation, because detonation is a shock wave having chemical energy release, and a specialized version of detonation in which no energy release that becomes shock wave. So it's very easy. We develop the theory for detonation wave and then we put the restriction, no chemical energy release, and we get the same equation would transform into the equation handling shock waves. Okay. So now about this reflection, we have already defined back in here, some important parameter called acoustic impedance. Now this impedance is the product of density and velocity. Velocity of sound times density. Now this acoustic impedance, some scientists or engineers, they define shock impedance and they replace this C with this shock velocity. Later I would show you that this C is related to this US also, so it doesn't matter. So you need not to be very much confused that acoustic impedance and shock impedance are totally entirely different. No, numbers would be different, the concept would remain the same. Okay, this acoustic impedance Z is product of density times velocity of sound, or it may be velocity of shock wave. Okay. Impedance increase means if we have larger impedance, it means that medium is less compressible. So if the impedance is higher, the compressibility is low. A very simple example.